In this video, we're going to make a super important connection between the standard free energy change of reaction ΔG0 and the equilibrium constant. This connection is so important because we can look at molecular structure to think about free energy. Ideas like stability, what makes a molecule stable, unstable, strain, charge stabilization, electronegativity, all kinds of things that you'll learn throughout your chemical education connect to the value of G. And ΔG0 specifically, relates to the equilibrium constant for chemical reactions involving some kind of structural change that changes the free energy situation. And so this connection is a very, very deep one and a very, very important one. The punchline is essentially given right here on the slide. For that standard reaction process that we defined in the previous video, which, if we just remind ourselves here, involved going from the standard initial state with Q equal to 1 to equilibrium, in which the concentrations of reactants and products have their equilibrium values, the standard free energy change of reaction ΔG0 is equal to -1 times the gas constant times the temperature in Kelvin times the natural log of K. I do have a couple of videos that walk through a proof of this equation, which is part of a law from physical chemistry known as the law of mass action. Really, it's a consequence of the second law of thermodynamics, but these proofs are way beyond the scope of introductory chemistry, so there's no need to check these out, but if you're curious, I have a couple of videos that I will link to on this topic. Now, this -RT natural log of K has a very similar form to the term related to Q that we noticed here. And I want to point out a couple of things about this to help the equation make sense. So this equation says ΔG0 is equal to -RT times the natural log of K. One thing that this helps us see is that if Q has a value that is equal to K, well, RT natural log of K, based on what we just said, is equal to -ΔG0, meaning the whole right-hand side here drops out and ΔG becomes 0. Ultimately, what this says in conceptual terms is that if we start with a system in chemical equilibrium, it is not possible to get any free energy out, or the reaction system cannot generate any free energy if it's starting in chemical equilibrium, right? Since it's already expended all of its free energy to get to chemical equilibrium, and if we just let it sit at equilibrium, it will just sit there, right? That's essentially the definition of chemical equilibrium. And so part of what the law of mass action helps us understand is that the free energy change for any reaction in a system at chemical equilibrium must be equal to 0. And we'll see what this looks like in specific contexts later in the course. The one I always think of is a dead battery. A dead battery is at chemical equilibrium and can produce no voltage as a result of that, right? Essentially, all of its free energy has already been expended. The redox reaction has run its course. Q is equal to K, and ΔG, the non-standard ΔG, starting from the equilibrium state, is equal to 0. A couple of other important conceptual points about this equation. When K is greater than 1, we think of that as sort of the product-favored situation, right? There are more products than reactants, more or less, at chemical equilibrium. The standard free energy change must be negative. This is worth pausing the video and verifying that if K is greater than 1, well, the natural log of K must be positive then, and so that -RT natural log of K must be negative overall. And we can conclude that starting from standard conditions, starting from Q equals 1, well, K is greater than 1 and Q is equal to 1, meaning the reaction proceeds in the forward direction spontaneously, starting from standard conditions. We often think about this the other way around, too, that if I know ΔG0 is negative, it follows from that that the equilibrium constant must be greater than 1 and the reaction must be product favored. The other side of the coin, if K is less than 1, well, in that case, the standard free energy change must be positive. Again, that falls out of the math of this equation at the top of the slide. And this means that if we start at the standard state, well, with K less than 1, the reaction will proceed toward reactants spontaneously. And so the reaction is non-spontaneous in the forward direction, starting from those standard conditions where Q is equal to 1. And so in addition to being able to apply this equation to do some calculations, for example, allowing us to relate a known ΔG0 to the value of K or vice versa, this equation gives us insight into how ΔG0 dictates the value of K and whether a reaction is product favored or reactant favored. Very, very useful insight, particularly given that we already know how to calculate ΔG0s using things like free energies of formation, heats of formation, standard entropies, and we can calculate K from those without ever doing any measurements of concentration, for example, right? We can do thermodynamic experiments to get this and infer the value of K as a result, and a lot of the equilibrium constants that you see in tables, for example, are done this way, using thermodynamic experiments to infer the value of the equilibrium constant without having to measure concentrations, some of which are very, very, very tiny for reactions that, for example, have very positive or very negative ΔG0 values. In this practice problem, we're asked to calculate an equilibrium constant, what's called the solubility product constant, we'll define that in a second, for AgCl using the standard free energies of formation of aqueous silver plus cation, chloride anion, and solid silver chloride. Now, I've gone ahead and looked up those free energies of formation, and they're listed on the slide in units of kilojoules or kilojoules per mole. Here is going to be a little more convenient to think in those terms. Actually, before we jump in and calculate the ΔG0, we should note that the reaction we're concerned with here is the dissolution reaction of solid silver chloride. So we're concerned with silver chloride solid being placed in water and dissolving potentially reversibly to form silver plus cation in the aqueous phase and chloride anion in the aqueous phase. And we already know from earlier discussions of chemical thermodynamics how to calculate the standard free energy change of this reaction given these free energies of formation. And I won't go through the detailed math on this. This is worth pausing and working out on your own. But if we apply this idea of product free energies minus reactant free energies, we end up with a value of positive 55.7 kilojoules per mole for the standard free energy change of this process. And what we're asked to do now is to infer the value of the equilibrium constant for this reaction, which is called KSP, from this standard free energy change. Now, before we jump into the math, let's back up a slide and note that already given just the sign of ΔG0, given that it's positive, we can infer whether K will be greater than or less than 1. With ΔG0 positive, well, this implies that K must be less than 1, so that the natural log of K becomes negative and this entire right-hand side becomes positive. So our KSP value is going to be less than 1, and in fact it's going to be way, way less than 1 as a result of this pretty endergonic, right, change in free energy, positive 50 kilojoules per mole. Okay, so we have an equation that relates the standard free energy change to the equilibrium constant, which we're calling KSP in this context. And actually, we need to do a bit of mathematical manipulation to get this equation in another form that is, I think, very important to understand and wrap your mind around as well. It's mathematically equivalent to what we've already seen, but it allows us to isolate K, the equilibrium constant, KSP. And so the way we're going to do this is divide both sides by negative R times T, and then raise both sides to e to the power of both sides, essentially, right? And so that will take the natural log of KSP and just turn it into KSP. And on the other side of the equation, we have e to the power of, or exp, negative ΔG0 divided by RT. And again, this is mathematically equivalent to the equation on the left. We just did some mathematical manipulations so that now we can calculate KSP directly from the known ΔG0. R here is going to be our usual 8.314 joules per mole per Kelvin, And the temperature here, we're going to assume this is just 298 Kelvin, pretty standard temperature. Let me just note, this should be 8.314. This will have the usual units of joules per mole per Kelvin. And then we do need to take care to make the units of the free energy change match the units of R. And so here, what I would do is something along the lines of 55,700 joules per mole, right? That's just the standard free energy change we calculated previously in terms of joules rather than kilojoules. So now notice we have just numbers inside, the argument of that exponential. And so we can plug in and chug along. Actually, before I just calculate out the number, I do want to note that inside the argument of that logarithm, we have e to the power of negative 22.47, which is going to be an extremely, extremely tiny value, right? We're looking at something like 2.5-ish to the negative 22 power. Very, very tiny, but that's what we expected, right? Based on this positive sign of the ΔG0 and the fact that the reaction is very endergonic, we should expect a very, very small equilibrium constant and a reaction that favors the reactant side. And just to get this in a bit of a different mathematical form that might give us intuition to how tiny this number actually is, this is equivalent to 1.74 times 10 to the negative 10. This is a value that you can look up in tables. We'll study solubility equilibria in detail a little bit later in the course, and this value agrees well with the number that you see in tables. And notice, we didn't need to do any concentration measurements to find this value, which is pretty neat, right? All we needed were these standard free energies of formation, which could be measured through calorimetric means, right? Thermodynamic means. We didn't need to measure any concentrations, and that would be really, really hard to do if my silver plus concentration is something like 10 to the negative 10, right? Or even 10 to the negative 5. Those concentration measurements would get very unwieldy. So this is a highly useful equation from an experimental point of view as well, but the most important thing is the conceptual connection between the sign and magnitude of ΔG0 and whether the equilibrium constant is greater than or less than 1, indicating whether the reaction is product or reactant favored. Here we have a heavily, heavily reactant favored situation. One insight that the connection between thermodynamics and equilibrium gives us is that as a reaction proceeds, as the value of Q, the reaction quotient, changes, as reactants are converted to products, for example, or products are converted to reactants, free energy changes. The free energy of the system changes, and the free energy of a chemical system in the equilibrium state is at a minimum. ΔG, remember, for the equilibrium state is 0, since the equilibrium state is already nature's end state, and it's not possible to extract any more free energy out of a chemical system that is at equilibrium. These graphs essentially make these points. And so what we're seeing here is a graph of the free energy of the chemical system as a whole as a function of reaction process for the three different possibilities for ΔG0. ΔG0 is equal to 0, positive, or negative. And I wanted to start with the 0 graph here. ΔG0 equals 0, we can tell because the reactants and products are at equal heights on this graph. And if we start, for example, with pure reactant, the free energy will fall, the free energy of the chemical system will fall as the reaction proceeds until we hit the equilibrium state at which K is equal to 1. And this is drawn on the slide, but just to emphasize it, K is equal to 1 here at the equilibrium state. And this is a free energy minimum. If the system makes a little more product or a little more reactant, the free energy will rise. This is true in all three cases, in fact. Let's now imagine the situation where the products are lower in energy than the reactants. This is very typical, right? A functioning chemical reaction is going to look like this, with the free energy of the reactants higher than the free energy of the products. One thing to note here is that again, as the reactants are converted to products, the free energy of the system falls. This actually follows from our non-standard free energy change equation that we looked at in the first video of this unit. And when we hit equilibrium, we're at a free energy minimum, but this free energy minimum is to the right of Q equals 1. Q equals 1 is in the middle of the graph, somewhere about here. And notice, at equilibrium, Q is to the right of that point, meaning K is greater than 1, right? This is typical of a situation with negative delta G naught, with the free energies of the products lower than the free energies of the reactants. The position of equilibrium sits to the right of Q equals 1 as a result of this negative standard free energy difference. And really, the reactants being lower in energy, free energy than the products, well, that's just the graph we just looked at, flipped, right? So I won't actually say too much about this. This is, again, the reactants lower in energy than the products, and so while the free energy will fall as those pure reactants are converted into products, the reaction will stop before we hit that Q equals 1 point, which would be, roughly speaking, right about here, Q equals 1, meaning K is going to be less than 1, right? We'll have more reactants than products, essentially, at chemical equilibrium, and this is, again, a consequence of the positive free energy change right here.